All right, this is section 2.3 of the Precalculus course. And in section 2.3, actually it's from 2.3 to 2.5, we're going to be talking about polynomial functions. In section 2.3, we're going to discuss polynomial functions and their graphs. So these again are the learning objectives. Please make sure you take these into account when you're reading through the e-text. And these are some examples I have set aside for us to work through. A few other additional ones as I do a little bit of explanation in my notes as well. So first of all, everyone should understand what a polynomial function is. Essentially, you have powers of x, and these powers are all positive integer powers. So, and then the a sub n, a sub n minus 1, etc., those are all real numbers, okay? So in this first simple example, we want to determine whether the given functions are polynomials. So this is actually a polynomial that is factored for you already. If you wanted to see it unfactored to be totally sure that we have all positive integer powers of x, you could just multiply it all out, and you see that this is a 6th degree polynomial. We call it a 6th degree as it's the highest power that we see. This is an example of a function that is certainly not a polynomial. Minus 3 divided by x squared is really the same thing as, there should be a minus sign here, sorry. Minus 3 times x to the minus 2. Minus 2 is not a positive integer power, nor is x to the 1/2, where the 1/2 is not a positive integer power either. So those are both reasons why this is not a polynomial. One of the first things we want to be able to understand about polynomial functions is to determine their end behavior. In other words, as x gets really big towards negative infinity or really big towards positive infinity, what's the end behavior? What is the function's graph doing? Is it going up or is it going down? So just kind of read through this and make sure you understand it. Essentially, just think about plugging a big number into the highest power of x that you see, and is that going to be a positive or a negative, and that's going to tell you whether it's going up or down. So in this example, we use the lead function, we want to use the lead coefficient test to determine the end behavior of f of x equals 6x to the 5th minus 3x cubed plus x minus 5. So we're talking about a function that's a 5th degree polynomial. The highest power of x we see is x to the 5th. So that is odd. So if I were to actually plug a really big negative number into that, that would still be really big negative, right? Think about x going to negative infinity. That would be close to negative infinity then. Times a positive number, it's still negative infinity, so you can see the end behavior down here is that it's going towards negative infinity. Likewise, if I plugged in positive infinity into x to the 5th, that would still be positive infinity times 6, which is positive, so it would go to positive infinity. So you can quickly determine the end behavior. You can memorize it this way if you want, but if you just think about plugging in a big number into the highest power of x, that kind of helps you find out the end behavior quickly. All right. The next thing we want to do is understand how to find the zeros of a function. In other words, where does the function cross the x-axis? Where is the function itself equal to 0? So if we have a cubic or less, there's a couple techniques, and the first technique is to think of the first two terms together and then think of the last two terms together. And that's the main technique that you will always use in factoring a cubic. So look and see if there's common factors in these first two terms, and we can see that there's an x squared term in each. So we factor out an x squared. I'm left with x plus 3, just working with these first two terms. Working with the last two terms, the only common factor is -1, so I factor out a -1, and then I have x plus 3. When this will help us is when I see now, when I think of these as two separate terms, these have now a common factor of x plus 3. So I factor out x plus 3, and I'm left with x squared from this guy and -1 from this guy, and I've been able to factor the whole thing because this is now a difference in squares. So it's x plus 1 times x minus 1. So the zeros here, when I set the function equal to 0, the zeros are x equals -3, -1, and 1, right? So that each one of these terms equal to 0. X plus 3 equals 0 means that x has to be -3, etc. If I give you a higher degree polynomial than 3, then you need to be able to factor out some power of x to begin with, right? So if you look at every term here, I see that I have an x squared is the common factor for all of these terms. So I'm going to factor out an x squared. And I'm actually going to factor out a minus x squared because I'd rather the next thing be positive, right? I'd rather try to factor a quadratic if I have the coefficient of x squared being positive. So when I factor out a minus x squared, I'm left with x squared minus 4x plus 4. I can see that that's the same thing as x minus 2 quantity squared, right? X minus 2 times x minus 2. So if I set that equal to 0, I now have the polynomial, a 4-3 polynomial, factored completely down into linear factors. Set it equal to 0, I can see that x either has to be 0 from this guy or 2 from this guy. Okay? Multiplicities and x-intercepts. So multiplicities are when you see a root, what is the coefficient of this guy? What is the coefficient of that factor? That's the multiplicity, this k value here. So if k is even, then the graph will touch the x-axis and turn back around. It won't cross the x-axis. If k is odd, the graph will cross the x-axis. And if k is greater than 1, even or odd, it'll still behave the way it does. But if k is bigger than 1, then what happens is the graph tends to flatten out near x equal to that root. So in the second example, we have this function f of x. This is a 5th degree polynomial, already factored for you. And you can see that the roots of this, if I were to set it equal to 0, is x equals 3 and x equals minus 1. X equals 3, though, that root has a multiplicity of 3. That's the power here. Okay? X equals minus 1 has a multiplicity of 2. So this is an odd multiplicity, which means that the graph does cross the x-axis at x equals 3. And also, since it's bigger than 1, we know that it flattens out a bit near x equals 3. This guy, x equals negative 1, has a multiplicity of 2, which means that it does not cross the x-axis. It touches it right at x equals minus 1 and turns back around and stays on the side of the x-axis that it was on already. But because it is bigger than 1, the multiplicity itself is bigger than 1. It flattens out near that value of x equals minus 1. Okay, same directions in this guy, except it's not factored. So here I want you to go ahead and use your technique again of how am I going to factor a cubic. Look at the first two terms together and the last two terms together. And I can see that in the first two terms, I have an x squared in both. So I factor it out. I'm left with x plus 3. In the last two terms, I have a factor of 16, a minus 16 actually in both. So I factor that out. I'm left with minus 16 times x plus 3. Then looking at this, I see that these two terms have a common factor of x plus 3. So that gets factored out. I'm left with x plus 3 times x squared from the first term, minus 16 from the second term. That's a difference in squares again, so I get x plus 3 times x plus 4 times x minus 4. So I have three roots here. If I set this equal to 0, I have x equals minus 3, x equals minus 4, and x equals 4. And they all have multiplicity 1, which means that the graph crosses the x-axis at each 0. All right, so if you want to graph a polynomial, and it's still an important, with technology, it's not as important as it used to be, but it's still important that you have an understanding of what a polynomial should look like. It'll help you when you're trying to do calculus and understand what's going on with the functions. So we want to determine end behavior, which we talked about. We want to find the x-intercept, which is the same thing as finding the roots. So solving f of x equals 0, which is what we've been doing, and use the multiplicities, which we just got to understand what happens near the x-intercepts. Then we want to find the y-intercept, which is easy because we just compute f of 0. In other words, the y-intercept is where is the function when x is equal to 0. And we use symmetry if possible, right? Whether it's an even function, so we have y-axis symmetry, or whether it's an odd function, so we'll have origin symmetry. And then also we can look at the maximum number of turning points. In other words, if it's a polynomial, it's going to be smooth and turn around, etc., etc. And the maximum number is n minus 1 if the degree is n. So for example, let's look at graphing this cubic. We understand that the general shape of a cubic is something like this, but we need to first determine the end behavior. The largest power is this guy. So if I plug in a negative number, this is still negative, so negative infinity. If I plug in a positive number, this is positive, so it goes to positive infinity. So there's my end behavior. I'm just putting a dotted shape in there just to kind of, fill it in, but I don't really know what that looks like. I just determined the end behavior right now. Okay, then we want to go ahead and find the x-intercepts. In other words, find the roots of the function. So this is a cubic. In this case, I don't have the 4 terms, so I just want to look and see if I can factor out some power of x, and there's a common power of x to the first power here. Factor out x, I'm left with this quadratic. X squared from here, minus 4x from here, 4 from here. That factors into x minus 2 quantity squared. So I have two roots. I have the root of x equals 0 and a root of x equals 2. X equals 0 has a multiplicity of 1, and x equals 2 has a multiplicity of 2. So we know the graph crosses at x equals 0, and at x equals 2, the graph touches and turns around and flattens out a little bit because it's bigger than 1. The y-intercept is when x equals 0, so f of 0, that's simple in this case, it's just 0 when I plug in x equals 0. I check for symmetry, so I plug in minus x, and I see that it's neither f of x nor minus f of x, so there's really no symmetry. And the max number of turning points here is 2, in other words, where it turns back around and goes in the other direction, because n was 3, it was a third-degree polynomial. And then just on the other side of the intercepts, I want to plot maybe some points just to get a feel for what it's looking like, okay? And then you can draw it in. So there you go.